Hello everybody, good afternoon and welcome to the Supergen Offshore Renewable Energy Hub webinar. Thank you very much for joining us this afternoon. Hopefully everybody who wanted to come has found their way in, but we've got a couple of others joining us as we go through. So anyway, my name's Deborah Greaves. I'm Professor of Ocean Engineering here at the University of Plymouth, and I'm the Director for the Supergen Offshore Renewable Energy Hub. And as part of our next phase of the hub, we're very delighted to have launched this webinar series. So we're running webinars roughly once every 2 months as a lunchtime event. And today we have some excellent presentations on the topic of design, particularly for floating offshore wind. And we have two very good speakers. Our own Tom Tostevin from the University of Plymouth, who's a research fellow at the Coast Laboratory, and also Francesc Fabregas Flavia, who's a senior engineer at DNV. And first of all, so we're going to have two presentations, each one about 20 minutes long, and then there'll be time for some questions. The whole thing will be take an hour, and we'd like to have you thinking about questions as you're hearing the presentations. Please do use the raise hand function if you'd like to ask a question in the meeting. This is being run as a Zoom meeting, so you can do that. Or alternatively, please do put your questions into the chat, and we will ask the questions from the chat as well. Okay, so I'd like to start off then by introducing Tom Tostevin, who's our Coast Research Fellow, as I say, at the University of Plymouth, and he's been working with us for a number of years, supporting the work of the Coast Engineering Research Group and the Coast Laboratory in physical and numerical modelling of floating offshore renewable energy devices. So over to you, Tom, and Tom's going to talk to us about the development of a short design event approach for speeding up the prediction of design loads for floating wind turbines.
Great, thanks. So yeah, my presentation today is on the development of a short design event approach. So as a one-sentence summary, what this is trying to do is trying to replace the 1 hour irregular wave and turbulent wind time series that are currently used in the traditional design approach with short 5 to 10 minute time series. And the purpose of this is to try and save some time and cost, and to try and open up the use of higher fidelity numerical models and improve the efficiency of physical tank tests as well. So the background work on this, on the hydrodynamics, was done through the Supergen RE Hub in support of work package 4 on design. And then what I'm presenting today, where we're expanding to the wind loading, was supported through an impact accelerator award, and is a collaboration between the University of Plymouth, DNV and Versity. Okay, so first I'm going to give a little bit of background on what the traditional sort of design approach is. So the traditional design approach has a number of design load cases which have to be evaluated, one of which that we've decided to focus on is 6.1. So this has the device modelled in storm 50-year return period storm conditions. And so this has the device in survival mode, so it's either parked or idling. So typically what would happen is a location would be selected and hindcast data gathered. So that's what this plot down here is showing. You've got significant wave height on the y-axis, peak period on the x-axis, and these grayed out dots are showing different hindcast data points. So a 50-year return period contour would then be fit to this data, and a number of sea states selected from the contour. So for each of these red dots, these sea states, would be simulating 6 1 hour irregular wave and turbulent wind time series. So that's 6 as a minimum. And then to get a design value, we take the maximum response occurring in each of those 6 simulations, take the average, and then multiply that value by a partial safety factor. So this can be quite time consuming. So within the fixed offshore wind standards, they have a method, constrained wave approach, where this can be avoided. So rather than using these 1 hour simulations, what you can do is you can constrain a nonlinear regular wave or a NewWave, which is basically just the average shape of the largest wave you'd expect to occur for that sea state, into a short 10-minute random background. So that's what this bottom right figure is now showing. We've got the random background wave given by the dashed blue line, the focused wave, the NewWave that's being constrained, given by the black line, and then the red line is showing that focused wave constrained within the random background. So this is permitted for fixed offshore wind. However, in the floating wind standards, the IEC and D&D standards, this method is not recommended because it's not going to necessarily be the largest wave that we would expect to produce the largest response. So this is kind of the motivation for the research is, can we come up with some kind of approach where we have an equivalent short design wave method that applies for floating devices. So just as a summary of the different types of waves and how long they take, we have the top figure is showing this traditional 1 hour irregular sea state. So we'd run 6 of these. The very bottom figure is showing what a single focused wave would look like. So on the y-axis, we're having surface elevation. And then the middle figure is showing what these constrained waves look like. So we've got the single focus wave at the bottom constrained into a short irregular background. And then some suggested time savings are given. So if we could use this constrained wave approach, then it'd be roughly 8 times faster than running the 1 hour cases. If we could run a single focused wave, it would be about 50 times faster. So these time savings, I should caveat, are based on looking at one response in a particular sea state. If we had, say, 8 different responses that all had a slightly different wave profile leading to them, then the constrained wave approach would not lead to any time saving. So these are the different design wave approaches we've looked at. The single focus wave, there's not actually a precedent for this in the design standards currently, but it's something that we've looked at because of the potential time savings. So the response conditioned approach that we've gone for, so rather than looking at the largest wave, we're using information from the linear response amplitude operators of the device for a particular response to come up with a wave and a wind profile that should produce the extreme of that response. So the inputs to this method are the C spectrum, and this is just represented by that top figure, and the RAOs, which I've just represented by this bottom figure. So here on this plot, you can see the C spectrum, the wave spectrum given by the black line, and then the response spectrum given by the red line. So as you can see, some wave periods are overrepresented in the response compared to just the background sea state. So in this case, if it's the pitch response that we're looking at, you see here between sort of the wave periods above 10 are overrepresented, and the wave periods below about 9 are sort of underrepresented. So this affects the shape, the profile of the wave that we would expect to produce the extremes. So using the RAO data, we can come up with this single focus wave given shown here as top right figure. So it's slightly different to the largest wave. And then we can also constrain this into multiple random backgrounds. So on this bottom right figure, we can see these grayed outlines in the background, the different realizations of this top wave constrained into different backgrounds. And you have the average given by the solid black line. So this approach is called most likely extreme response wave approach, and it's taken from ship design. So what we've done is we've applied this, and we've also extended it to the wind loading by treating the waves in the wind as independent Gaussian processes. So that's the method. What we did in this study is we looked at 8 different devices in OpenFast. So we wanted to cover the 4 main platform types to see how applicable the method is across a range of different scenarios. So we've got 3 semi-subs we looked at, 2 spars, 2 turbine platforms, and a barge. And a couple of different turbines, some of them are 15 megawatts, some of them are 5 megawatt. And then I'd like to acknowledge our gratitude to the Carbon Trust Floating Wind JIP for letting us use a couple of their designs to extend the cases that we could use for the project. So we looked at these 8 different devices, and we looked at 2 sea states. So one is a bit more extreme, significant wave height of 10.7. One was a bit for a much more sheltered location, significant wave height of 5.1. So for each of these devices in these 2 sea states, we modeled 10 1-hour irregular wave cases, and then we also modeled 20 constrained response conditioned events. And we did this for 4 different responses. So the pitch, mooring load, nacelle acceleration in X, and the tower-based bending moment. So as a summary, we looked at 8 different devices in 2 sea states, and we modeled 4 different responses. So we're trying to get a wide range of cases to see the applicability of the method. So this is just to illustrate how we can check if the method is performing as we think it should. So what this plot on the left is showing, we've got surface elevation on the y-axis and time on the x-axis. So we've taken the 10 1-hour irregular wave time series, and this is for one of the Spar devices looking at the extreme tower-based bending moments. So what we've done is we've taken those 10 1-hour irregular wave cases, and we've aligned the time series so that the maximum tower-based bending moment occurs at 0 seconds. So we can see here that if we take the average of this wave profile given by the solid black line, there's a clear pattern, a clear average profile that's leading to the extreme response of the tower. So if we are using this response condition method, we would expect the wave profile that we produce from that to match this. And we can do exactly the same thing with the wind. So here we have the 10 different background cases given by the background lines, and then the average wind profile given by the solid line. So after that, we've taken the RAOs for the device and produced these response condition profiles. And when we overlay them, you can see that they match well with the empirical profiles that we've come across. So this is an indication that it's working as we expect. So say here, this is the constrained. This red profile is the average of the 20 constrained cases. Okay, so just because the profiles match up doesn't necessarily mean that the results are going to be the same. The design value estimates might not necessarily be the same, so we need to check that. So this figure takes a little bit of explaining, but the most important part is the y-axis. So this is telling us how much of an over or under prediction the design value estimate is from the constrained cases compared to the traditional irregular wave method. So if the y value is 1.1, that would tell us that the short design event method has over predicted the design value by 10%. If it's 0.9, it would tell us that the short design event method has under predicted by 10%. The x-axis here is giving what we've termed the relative importance. So this is like the ratio of how important the wave loading is compared to the wind loading, and we calculated this based on the RAOs. So an RI value of 4 means that if we were to run a wave-only simulation, we would expect the extreme response to be 4 times larger than the extreme response if we ran a wind-only simulation. And yes, this is calculated from the RAOs in this case for the pitch response. So you can see each of these markers gives us one of the 8 different devices. We have the spars are given by circles, the semi-subs are given by triangles, and the TLPs are diamonds, and then the barge case is a square. The bars are then showing the 95% confidence intervals on these estimates. So you can see here for the pitch response, the short design event method is producing values sort of between -5% under prediction, sort of 15% over prediction in terms of these mean values. So we would also like to see all the responses grouped. So here we have similar plots, but this time all the responses are plotted. So for each device, so if we say this diamond here, we've got 4 of them there, because that is for the mooring load, the pitch response, the static acceleration, and the tower-based bending. But they're not distinguishable on this plot. We've just got it as a scattered so that we can see the range of applicability. So on the left-hand plot, we've got the constrained, the short design event method, where we've got the 20 constrained cases, and on the right we've got the single event. So for the constrained cases, you can see that the range sort of goes from -5%, so 5% under prediction, to just over 20% over prediction. And then for the single event, it's a bit wider. Part of this is because some of these lower cases are for the mooring load, and we wouldn't necessarily expect a single event to be able to produce the extreme mooring load, because the background wave is important. So a single focus wave on its own isn't, we wouldn't expect it to be able to produce the extreme. So the sort of applicability of different methods is partly dependent on the response that we're looking at. So yeah, overall similar range with some lower cases for the mooring loads. And then we've plotted this relative importance. So in the blue region, the waves are more important. In the red region, the wind is more important. We don't actually see much of a trend. It seems to work similarly in both regions. So as a summary, we've come up with this short design event method for predicting design loads. The single short design event, so like the single focus wave, is less accurate for some responses, so it needs to be used with caution if thinking about mooring loads, particularly for semi-subs and barges. And then overall, the constrained cases, we had results within roughly -5% to +20% of the traditional method. So future work, we're in talks with DNV on how what the success criteria kind of should be for a method like this. So whether or not it can be included into recommended practice and design standard documents as it is, or whether more refinements are needed. And we've also started to look at other cases. So this was just design load case 6.1, where the turbine is parked in an idling conditions. We've also looked at some cases where the turbine is operating. And so I was just going to finish on just a video of how we've applied this approach during physical experiments recently. So this was for the extreme pitch response. So you have this was in the coast lab. We've got the semi-sub, the alternus model, and we've got a thruster system simulating the wind loading, and then a single focus wave event coming in. So this is for the maximum pitch response. It's carrying. Okay, so very short if we're looking at the single approaches. And then I suppose the other part that we still need to look at is a similar sort of analysis, but rather than for the floating device, looking at the fixed device and how the constraint wave method already recommended in the fixed standards compares in terms of the underestimation and the overestimation. And so yeah, thanks for listening. That's my contact there if anyone has any questions.
Okay, thank you very much, Tom. really interesting presentation. Can I, we've got time now for some questions, so can I ask for people to either use the raise hand function, which you can find down if you press the reactions thing at the bottom, or alternatively, you know, feel free to just unmute and ask your question. So let's see if we've got any questions from the audience, please. Perhaps I'll just start off with a quick question myself for Tom. So you mentioned applying this to fixed devices as well. Do you think what would you expect to see? Where would you expect to see differences?
I suppose I'm sort of expecting the range of, so like when I plotted those confidence intervals, expecting to see maybe narrower confidence intervals and smaller underestimations and overestimations potentially. But it'd be interesting to clarify that, because it's not something I've seen in the literature, that kind of analysis.
Yeah, absolutely, and some more experiments as well, I think, because this is all the numerical modelling that you've used for this is linearized, isn't it? Or could you say a little bit more about that? Sorry, how much of the non-linearity is included in these simulations?
So the simulations are using open fast, and it's all using linear wave theory. But it is for some of the models, it's including the quadratic transfer functions, so the second order sort of low frequency surge and lower frequency pitch responses. But yeah, there are those kind of models aren't perfect at picking up the nonlinear effects, so it's important to do the physical experiments as well, because we do see some differences when we do physical experiments compared to the numerical models.
Okay, thanks very much, Tom. And we have a question from Emma. Hi, Emma.
Yes, hi. Thank you very much, Tom. That was a really interesting presentation. My question was about your plot with the RI values for the different types of platforms. I think, so I guess a lot of these are kind of different size wind turbines, so there'll be different size platforms. And I was just wondering if you kind of think that the larger RI values are to do with the platform itself, or the differences in size of the platforms and wind turbine capacity.
It's not something I've put a huge amount of thought into. So I think there are also some limitations with the way included some of the terms in the open fast model. So I was using a drag coefficient on the tower of 1, and if I'd used a smaller value of 0.5, 0.6, it would have shifted everything to the right a bit into the more important wave sort of region. But I think it was good to do that so that we have a wider range of cases to study. Yeah, I didn't notice any significant trends. Maybe, I suppose, for the smaller turbines, I guess it's the same wave conditions, we'd maybe expect the wave to be more important for the smaller turbine cases. But yeah, there wasn't much in the way I could discern about trends between the different devices or the different sizes. I guess the main one was that it seems to work better in general for TLPs and Spars. I suppose they are sort of less dynamic than the semi-subs and the barges. So if it's the linear RAOs, a description maybe for those cases.
Thank you.
Thanks.
Okay, thank you very much. Do we have any other questions for Tom? Okay, if you have a question for Tom that comes to your mind later on, you're still very welcome to use the chat and put questions for Tom into the chat, and he will be staying with us. So if there are questions at the end, there'll be a chance to ask then. But I think we'll move on to our next speaker, and again say thank you very much, Tom, for your presentation.
Thanks.
I'm just going to try and give you a round of applause. So thank you, thank you very much, Tom. And we'll move over to Francesca next. So thank you very much, Francesca, for joining us today and for offering to do a presentation. And Francesca is the senior engineer at DNV, working as a specialist for numerical modelling of floating wind systems. And I'm delighted that he's joining us, and he's going to talk to us about floating offshore wind design, tools and challenges from an industry perspective. So thanks, Francesca, and over to you.
Thanks, Deborah. First of all, can you see my screen? Can you hear me well?
Yes, that's fine. That's all good.
Cool.
Yeah.
Great. Yeah, thanks for the introduction. So in the next 15-20 minutes, I'm going to try and outline some of the challenges that we're seeing when it comes to design of floating wind systems, especially looking at the tools, the software, and also the methodologies. So just to set the scene a little bit, because the topic of the presentation is quite generic, we could look at some of these challenges from the point of view of a large array. Then we would see that things like the optimization of the cabling layout, the use of shared mooring systems, novel methods for doing operation and maintenance installation are all relevant, and they all come with their challenges. I'd like to also mention wind farm control, because this has received recently quite a lot of attention. There's a joint industry project, JAP, led by DNV, looking at validating some of the models that have been developed for many years, looking at interactions between turbines with the objective to maximize the energy captured by the whole array. So here we're looking at the array as a power plant instead of looking at each individual unit. So I'm not going to talk about in detail all these topics, but I'm going to focus on a single unit, the design of a single unit. This is also to reflect the fact that the industry, well, it's coming of age, still at an early stage. So we're seeing deployment of a few units, but we're not yet at the stage where these are deployed into very large arrays. So I'm going to talk about three main challenges that I've grouped into a category called physics, interfaces, and efficiency, but I'll explain that a bit more detail in the next slides. So I think that the first point I wanted to make is that the floating wind industry, although it's developing faster, is still at an early stage compared to other industries. And we see a lot of prototype development, which means that the structures are actually not fully optimized, but they are in a way incorporating quite a lot of conservatism of demonstrating purposes. We see lots of R&D. And one important point is that the design workflow is not fully established. We see different tools, different methods being used by different people. Therefore, this is a challenge in itself, and further effort is required to compare these different workflows, tools, to see what are their advantages, disadvantages, and also the need for further development. So when I talk about workflow, I'm just going to show here briefly what I'm referring to. So normally for the design of such systems, we start with catapult analysis, looking at the integration of the structure itself with the control action with aerodynamic loads, hydrodynamic loads. And then we have kind of an intermediate step where we're trying to map some of the loads that we derive from this capital analysis onto the structure before we can actually perform detailed structural analyses. So currently, as I was saying, there's no standardized way of kind of go from the left to the right. There are different approaches. So I'm going to talk about some of the challenges with these different approaches, especially for the first two steps. So when it comes to capital analysis and then this local load mapping. So starting with the capital analysis step, there has been quite a lot of effort to develop and also compare these hydroservo-elastic tools to carry out capital analysis, but we still see that we have a range of tools. Some of them coming from the oil and gas industry legacy, so offshore design tools like SESM from DNV, general FEA tools like ANSYS, and some marine dynamic tools. All these, as I was saying, come from the oil and gas industry, and they are quite good at predicting advanced hydrodynamic loads, also modeling marine operations that are quite important for floating wind. But maybe as weakness, they're perhaps less advanced to model complex plate dynamics, turbulence, aerodynamic loads in general, compared to other tools which come from the onshore sector, like bladed from DB, some other in-house aeroelastic tools used by some OEMs, and then also some other open source academic tools. So like, from this is not an exhaustive list, but we can see that we've got different options, but none of the options is perfect. So what that means in the end is for design within a project, we might be using several of these tools at the same time for different purposes. If we're looking, for example, at moorings or the floater, we might use some of these tools coming from legacy oil and gas. But to design the turbine, look at the tower loads, we might use these aeroelastic tools instead. So this poses some challenges, especially in terms of time spent creating different models, aligning them, running them in parallel. All this is quite complex because each of these tools are based on sometimes different models, different assumptions, and the number of parameters involved is quite significant. But the other challenge is not only the fact that there exists a number of them, is also that, as I said, they come from legacy oil and gas or onshore wind, and these systems, whilst they are in a way similar to the floating wind turbines that we see nowadays, they present some differences, and that's something that I wanted to kind of show a bit more on this next slide. So we see more and more novel designs being presented for floating wind systems that try to optimize the mass, for example, of the floaters, and some of them rely on weather vaning concepts, so meaning that they can align with the wind direction automatically. Some of them include some airfoil-shaped towers. And in terms of modeling challenge, these structures are more difficult to model than others that don't undergo these large displacements when the wind direction changes, especially if we're modeling them using traditional BEM hydrodynamic models that assume that the displacements are small compared to the equilibrium position of the system, for example. Another example of these novel systems is this T-omega design, which includes some non-uniform cross-sectional buoys, which in this case introduce quite a lot of nonlinear hydrostatic loading. So this is something that most of these legacy oil and gas tools do not incorporate, and therefore there's a need for further development to be able to represent as accurately as possible the dynamics of these new systems. So these are two examples from the hydrodynamic side of things, but there's also work done on the aerodynamics as well, because as opposed to fixed turbines, onshore or offshore, floating turbines are more prone to undergoing misalignment with the incoming wind direction, operating in stalled conditions, and therefore these dynamic effects, although they can be accounted for with, for example, dynamic stall models, when we have situations where these angles of attack become quite significant, we've seen that the traditional dynamic stall models do not perform very well under these large stall conditions. And here in the middle of the slide, you have an example showing the lift coefficient variation on the y-axis as a function of the angle of attack. So these are hysteresis loops for different mean pitch angles. And you can see the black line is the experimental trend, and this red line that matches quite well the experimental trend is a new dynamic stall model that has been developed and implemented in bladed, and that outperforms the other kind of traditional dynamic stall model used in the onshore industry, which is the Beders-Leishman model that is in dark blue in these figures. So we see there's a need to improve the existing tools. So that's what I was trying to highlight in this slide. So normally in industry, the tools that are often used are these hydroserve elastic tools, because they provide results with enough accuracy with a relatively low computational time, at least compared to more sophisticated tools like Brand solvers or even smooth particle hydrodynamic solvers, which are more the realm of academia and R&D. But because of what I mentioned previously, there is a need in combination with experiments to sort of use these higher fidelity tools and experiments to improve these engineering simplified models that we use for industrial applications. But you can see in this plot, there's a gap, and that's on purpose, because these hydroserve elastic tools, even if they are less computationally expensive than the other ones, they are still too expensive if we are at an early design stage where we need to iterate fast the design. We need to evaluate lots of design loops. And for this sort of stage of development, there are other tools that are based on frequency domain approaches that are more suitable. And a lot of effort is put on these type of tools at the moment in the industry to help perform quick design iterations. So just to show an example of that, I said to be able to perform these redesign loops quite quickly, here I'm showing an example with one of these frequency domain tools that has been developed at DNV called Renewables Architect, where we see an initial floater design for a given turbine size, water depth, and environmental condition. And what we're trying to do is to evaluate the change in the cost and the design of this floater if we had some constraints when it comes, for example, to the floater width. And so using this type of methods, we can iterate the design, so vary the separating distance between the columns, the diameter, the draft, et cetera, to find a configuration that matches the constraints, so the maximum width, but that also ensures that the nacelle accelerations, the tilt angle of the platform, et cetera, is within the limits that we as designers specify. Right, so this is sort of an overview of some of the challenges associated with this scaffold analysis right now. Now I wanted to focus more on this intermediate step where we are sort of taking the loads from this scaffold analysis and applying them to the floater to perform the structural analysis. And here we see there are different methods applied in industry, but there has been little verification or validation, cross comparison between them. And therefore, there's a need for this. The methods depend on the stage we're at. So we can be looking at initial sizing of the system, in which case we're probably going to make some assumptions, limit the number of cases, simplify the turbine model, for example, or we can be on the other end of the spectrum, looking at a detailed design case with 15,000 load cases and a detailed model of the turbine. So I'm going to briefly talk about two of the common methods used for these two phases. One is the load mapping using a beam model, and the other one is using a rigid body model. So starting with the beam model first, as the name suggests, in this case we're looking at a representation of the structure, in this case the OC4, in this example, using beams, flexible beams. And these beams are connected to hydrodynamic bodies, which can be PEM bodies, so radiating or diffracting bodies, or instead Morrison bodies as well. And what we're doing is we are solving for the loads, the cross-sectional loads in this beam model based on these loads, and then using simplified analytical expressions to calculate stress levels. So although this might seem relatively straightforward because of the simplicity of this beam model, actually there are a number of challenges associated with creating this beam model in the first place. And one of them is joint flexibility. So I'm showing here a real example from one of the projects that I've worked on recently. It's not using this OC4 geometry, it's different floater, but we were looking at predicting the coupled frequencies of the structure in both the side and fore-aft directions. And we were using a beam model that was taking into account local joint flexibilities. So on the right-hand side here, you can see a joint, the intersection between two beams, and as a result of the application of a load, there's one of the beams that's deforming. So this is introducing some changes in stiffness locally at this joint. So we created a model, a beam model that accounts for that, and then another one that does not account for this local joint flexibility. And we compared the coupled frequencies against the prediction from the finite element model. And what we saw was that the local joint flexibility was quite important to predict these coupled frequencies. So we had the percentage difference of 9%. That is actually in the end important for control design. And then also, when you think about the process of creating this beam model, you start with a detailed representation of the structure. So it's not straightforward to go from this detailed representation to something that's much more simplified. And yeah, so another challenge, in addition to this joint flexibility, is also how to consider hull pressure in the first place when estimating the stresses. So that's something that gets missed when using this beam model approach. So looking at the other one, which consists of considering a single rigid body or multiple rigid diffraction radiation bodies and mapping the hydrodynamic pressure onto the structural mesh to calculate stresses. As you can see in the example here, we have this OC4 platform and this orange lines show the mesh on which we've mapped the hydrodynamic, the hydrostatic pressure as well. And the varying colors here show the stresses. This is the result of the structural analysis. But in this case, these columns are considered to be fully rigid, as opposed to the beams that are connecting them, which are deflecting. Deflections there are exaggerated. So in this approach, the challenge is because we are using the assumption that these large bodies are rigid, one of the challenges is how to account for flexibility in case we had a concept where the columns might not be considered fully rigid if hydroelasticity was important. And then I'd say one of the most significant challenges is how to map the hydrodynamic or the hydrostatic pressure efficiently on these rigid bodies, given that we have thousands and thousands of load cases, so a very significant number of time steps that involve a lot of computational burden, but also data. So I wanted to sort of conclude this presentation showing some of the developments, the effort that's been made on DNV side to kind of tackle some of these challenges that I was talking about. And these are results that were presented recently on sort of improvements in the efficiency of these software tools that allow the user to carry out structural analysis, detailed structural analysis in this case. So on the left-hand side, you can see the workflow that I was showing before. So starting with coupled analysis, going to more detailed structural analysis. And on the right-hand side, you can see the reduction in computational time, just more than 60%, for the latest releases of some of these structural and hydrodynamic software. And I've highlighted here in red the fact that this 60% reduction in computational burden is based on an example with more than 100,000 time steps, which is, again, quite significant for these cases. So this is looking at detailed design. In parallel, also, we've been working on developing frequency domain models to predict these fatigue and extreme loads on the floater a lot more rapidly than with these more detailed time domain approaches, just to allow the user to iterate the design at a very early design stage. And something that I mentioned that's quite important as well is the fact that this is enabled by the cloud. So because we have such large numbers of data to deal with, it's quite interesting to use the cloud to make use of as many CPUs as possible for these calculations. So finally, for me, some of the key takeaways are that we haven't got an established workflow. There are different options, different tools, different parties using different things, and therefore there's a need for comparison, for validation, to increase confidence in each of these methodologies. We have developments in the time domain, but also in frequency domain quite recently to look at how we can optimize these structures more efficiently. And therefore, based on what I mentioned, I think we can group these challenges into 3 categories. So one category, physics, we need to further develop these tools, as I said before, to model aerodynamic, hydrodynamic features, for example, more accurately than we're currently able to do with the existing tools. We need to improve the interfaces because these tools are going to continue to exist and develop in parallel. So different people will use different tools. So we need to improve the coupling between them, improve the interfaces. And finally, in relation to what I was saying, for floating wind design, we need to account generally for thousands of load cases. So improving the efficiency of the data management and the computational burden, especially when looking at detailed design, is really important. So these are some of the challenges that I wanted to outline. And if there are any questions, please, share in the chat or.
Okay, thank you so much, Francesc. That's a really fascinating presentation, and yeah, really nice to see those developments and the perspective of different design stages and so on. So let's move to the questions. You say there's a question in the chat there. Do you want to respond to that one first? Does the 9% frequency difference refer to the difference between the finite element method result and beam element result?
Yeah, exactly. That's right. So, so this is comparing the coupled frequency derived from an FEA model that accounts for all the complex features of the structure, the scantlings, everything, compared to the simplified beam model. The slide was showing that these local joint flexibilities are quite important to predict the same coupled frequency that we would obtain using an FEA model.
Okay, thank you, and thanks for the question, Kobe. And Majid, would you like to unmute and ask your question?
Yeah, thanks. Thanks for this very interesting presentation. I have actually 2 questions. The first one is about where you discussed about the misalignment on the rotor because of the floater motion and the dynamic stall and all these problems that we deal with. From your point of view, if you can just let us know how significant you think those misalignment would be, I think that would be useful. And another question I had was about the frequency domain analysis, and I was wondering if you can provide more information how it can capture the coupled nature of the aerodynamic side and the hydrodynamic side, how you can capture that using these tools. I think that would be appreciated. Thank you.
Thanks. Yeah, interesting question. So yeah, the first one about this misalignment. So for this, especially for these single point mooring systems that can weather vane, for certain load cases, we see that the load cases, for example, like DLC 1.4, where we're looking at direction change of the incoming wind, we see that the change in position, if we're looking at the yaw angle, can be significant, can be 30 degrees or more. So in this case, to model this transient with BEM theory can be challenging. So that's what I was sort of trying to refer to in this slide, that there needs to be more development to actually test and validate these tools for these challenging cases. And so in relation to the frequency domain models, one of the things that we're looking at the moment is how to convert a detailed model of a turbine into something simpler, a mass spring damper system that can be coupled with these frequency domain models to at least partially account for the coupling between the two. Although, there's a price to pay, I would say, for the fact that these models of frequency domain run much faster, is that we cannot have the same level of accuracy that we would have with the time domain models.
Fair enough. Thank you so much for answering.
Okay, thank you. Thank you very much, and thank you for the question as well. We have run out of time now, so but I think that was a really fascinating pair of presentations. So thank you very much to Francesca and also to Tom. The presentations will be available, the recordings will be available on the SuperGen website, so you can always come back and have a look at those there. So please do that. And then the other thing I need to say is that our next seminar is going to be on Monday, the 11th of March, also 1 till 2 o'clock. And that one will be around the area of the impacts of wind energy extraction on the physics of primary production in Scottish and shelf waters. So looking at the ecosystem impacts of offshore renewable energy. And there'll also be some presentation on the Pelagio project, and this is Beth Scott and her team up in Aberdeen. So thank you very much, everybody, for joining us today. Please do join the next webinar from SuperGen, which will be, as I say, in March, and you can see the recordings on the website. Thank you very much. Goodbye, everybody. Thank you.